Hey there, peoples. What up? In this video, we are going to be solving radical equations. In the last video, we solved rational exponent equations, and now we're going to go just straight to solving radical equations. So before we get into solving radical equations, we need to think about inverse operations. Every time that we solve, in order to get your variable equal to a very specific number, we needed to use inverse operations. So for example, let's pretend your equation had addition next to the variable. To undo that, we had to use the inverse operation subtraction. Another inverse operation you could use is if you're multiplying two things together, you can divide them to undo them and vice versa. So I want us to think about how would you undo a square root? How would you undo a cube root? How would you undo a fourth root? And I just want you to take a second to think about how do these type of radicals, quote unquote, break free when we're simplifying them? And how can we extend that idea to get rid of these radicals in our expressions? So hopefully you've had a moment to think about it. And when we're breaking down square roots, you know that groups of two based on this index here break out of this square root, right? If this was the square root of 25 or something, you know that you can break down 25 to 5 times 5. And so groups of two break out of there. And we could rewrite this as 5 squared, really, right? So the idea behind undoing a square root is it's based on that index. We could realistically square the square root, and that would mean the square root of x times the square root of x. And by the product property of radicals, that's x times x under one big one. And look, groups of two, it's going to break out and just be x, right? Got rid of the square root. Can we extend that idea to a cube root? Look at that index, 3. If I raise it to the third power, that's cube root of x times the cube root of x times the cube root of x, which is really product property of radicals. Cube root of x times x times x. Groups of 3 break free of a cube root, and we get x. If you were to extend this pattern, how would you undo a fourth root? Hopefully you were noticing that to undo a square root, we squared it. To undo a cube root, we cubed it. So to undo a fourth root, we would raise it to the fourth power. And by the same idea, we would end up getting just x. We are 100% going to use this idea as we work through solving radicals. So just like there were 3 steps to solve rational exponent equations, there are also 3 steps to solve radical equations. Step 1, isolate the radical expression. That means get the radical 100% alone by itself on either side of the equation sign. Step 2, raise each side to the power of the index. So square roots, cube roots. Raise each side to the 4th power if you have 4th roots. Lastly, you have to simplify and solve for the variable, and this can increase in difficulty depending on the type of equation that we have. So let's hop on into a couple examples. Our first example says, solve 5 is equal to the square root of n. So we first want to make sure that we isolate the radical expression. So, grab your radical expression, find the radical, and put a box around it. Is it alone? If the answer is yes, it is isolated. Step 2, raise each side to the power of the index. So since this is a square root, I'm going to square the left side, and whatever I do to one side, I have to do to the other. Now I'm going to have 5 squared on the left is equal to n, and we know what 5 squared is. That's 25. Oh my goodness. We are done. We finished. Simplify and solve for the variable was the last step, and it really took a hold of itself. One thing that I actually didn't write on the steps here is that you have to check for extraneous solutions, meaning we have to check for things that end up lying to us, just like your x, extra solutions that aren't really true solutions. So we also need to check for extraneous solutions. And when we check, we have to check in our original problem. We have to check 5 is equal to the square root of n, but now we're going to plug in that n was 25 and see if this is true. Is it true that 5 is equal to the square root of 25? Well, yeah, square root of 25 is 5. So this really works out. Always got to check for extraneous solutions. Step 4. Go ahead and try problem 2 on the right-hand side. The square root of 16b is equal to 4. Don't forget to check for extraneous solutions. Okay, did you get b is equal to 1? If so, you would be correct. Again, step 1, isolate the radical. Already accomplished. Step 2, raise each side to the power of the index. Now, even though it doesn't have the little index number right there, we know square root, we're going to square both sides, meaning raise it to the second power. You end up getting 16b is equal to 16. Pro tip, when you square a square root, you get the radicand. So that's why you get all of 16b on the left-hand side. So we have 16b equals 16, divide both sides by 16, you get b is equal to 1. Don't forget to check for extraneous solutions as shown below and make sure you get a true statement before you officially say that that is the solution. Now, let's work on slightly more difficult problems and apply the same steps. So here's our next set of problems. We are going to have a square root equal to a square root. This is the next level. So notice both of these problems have square roots equal to square roots. So we're still going to follow our procedures. We're going to make sure that the radicals are completely alone here. So radical equal to a radical. Radical equal to a radical. Perfect. They are isolated. Then, since they're square roots, we're going to square both sides, raise them to the second power. The left side, we're going to get 7k is equal to 6k plus 1. When you square a square root, the result is the radicand. And from here, it's just business as usual. If I want to solve until I get the variable alone, I'm going to subtract 6k from both sides, and I end up with 1k is equal to 1. Perfect. Now, before you decide that that's the answer, don't forget, check for extraneous solutions. And when you check, you have to check in the original problem. So here's the original problem. I'm just putting a set of parentheses for every variable that was there. And I'm going to check k is equal to 1. So my question is the square root of 7 equal to the square root of 6 plus 1? Well, yeah, that's going to be the square root of 7 equal to 7. So yes, k is equal to 1 is truly the solution. You tried the problem on the right. Did you get r is equal to -4? If so, you would be correct. If not, take a second to pause this video and double check all of your steps. Did you square both sides? You would get 2 minus 2r is equal to 6 minus r. Then use your inverse operations to solve. You didn't have to do it the exact same way as I did, but regardless, as long as you're following the rules of algebra, you should get r is equal to -4. Now, don't forget, you do have to check for extraneous solutions as shown over on the right, and you get a true statement like the square root of 10 is equal to the square root of 10. Awesome. So there's going to be one more type of problem that you're going to encounter when solving square roots. And this one is a little bit tricky. So here we have a square root plus like a number is equal to a variable. Okay, this one's just a little bit more complex, but the steps remain the same. So step number 1, isolate the radical. Get it completely alone. Notice that our radical is not alone on the left-hand side. There's a +1 over there. So we need to subtract 1 to get it completely alone. This is going to leave us with the square root of 6x plus 21 is equal to x minus 1. Okay, isolate the radical. Perfect. Then raise each side to the power of the index. Since this is a square root, we're going to square both sides. And this is where things get tricky. The left-hand side is squaring a square root, so we're going to get the radicand, 6x plus 21. But what's tricky is x minus 1 squared literally means x minus 1 times x minus 1. So I want you guys to physically write this out, because when something is squared, that means you have to multiply it by itself 2 times. And the trick here is we're going to need to FOIL. X times x gives us x squared. X times negative 1 gives us negative x. Negative 1 times x gives us negative x. And negative 1 times negative 1 gives us positive 1. And here's what you guys are thinking. Oh no, there's an x squared. In order to solve this problem, I have to use my second favorite F word. Factoring. Keeps coming up again, you guys. I told you it never really goes away. So if I simplify this, 6x plus 21 on the left is equal to x squared minus 2x plus 1. In order to solve this, because there is an x squared term, we have to factor this. You must factor this to solve this equation. Factor it. So in order to factor it, I'm going to move everything to one side. So like I'm going to subtract 6x from both sides. And I'm going to subtract 21 from both sides. If I do that, my resulting equation is going to be 0 on the left, x squared on the right, negative 8x, and minus 20. Negative 21 plus 1 is negative 20. And so I don't know if you guys remember factoring, dude. We have to figure out what multiplies to the last term, what multiplies to negative 20, but adds up to negative 8. What multiplies to negative 20, but adds up to negative 8? And that's going to be 2 times negative 10. So to factor this, and remember, this guy is like x times x. This is going to become x plus 2 times x minus 10. And of course, it's equal to 0. And by the zero product property, set each of them equal to 0. You'll get x is equal to negative 2 as one of your options, and x is equal to positive 10 as one of your options. Now, don't forget, you have to check both of these answers for extraneous solutions. So you have to plug them both in to figure out if they're true or false. And up until this point, really, when we were checking for extraneous solutions, we never came across a problem that gave us a false statement, that gave us a lie. So let me show you what it will look like when you do get an extraneous solutions, because one of these numbers is in fact extraneous. So if we're going to check these, hold on a second, I'm going to erase all the stuff on the left side just so that I can have some space to show you checking for extraneous solutions. I'm telling you that factoring keeps coming back even when you don't want it to. Okay, so before we decide for sure which ones work, we have to check. We have to check that they're not extraneous. In the original problem, the square root of 6 times x plus 21 plus 1 on the outside is equal to x, okay? So we're going to plug in negative 2 first. It's just the first number that appears there. So if I plug in negative 2, everywhere there was an x in my original problem, I end up getting 6 times negative 2 is negative 12 plus 21 under my radical, plus 1 on the outside is equal to negative 2. Negative 12 plus 21, that's the square root of, that becomes 9. So the square root of 9 plus 1, is that equal to negative 2? And then square root of 9 we know is 3. Is 3 plus 1 equal to negative 2? No, this is actually 4. And since this is not true in any way, shape, or form, x minus x is equal to -2 is extraneous. It is not a true solution of this problem. Now we're going to need to check x is equal to 10, and you want to check them both every time because you could get no extraneous solutions, one extraneous solution, or potentially have two of them be extraneous solutions. So it's really important that we actually make sure that we go back and check both of them. Don't get lazy and just call it quits. So we're going to plug in x is equal to 10 here. When we do so, we're going to have the square root of 60 plus 21 on the outside, plus 1, and hopefully that's equal to 10. This becomes the square root of 81 plus 1 is equal to 10. Square root of 81, is 9. 9 plus 1 is equal to 10. And you know what? 10 is equal to 10 is a true statement. 10 is equal to 10 totally works. So x is equal to 10 is the true solution to this problem. So here's your chance to try and see if you can solve this square root. Think back to the last problem and try to replicate it with these variables and numbers. See if you can solve it, and I'll see you in just a second. All right, so hopefully for this problem, you isolated the radical by adding n to both sides, squared both sides to get rid of the radicals, and when you did, you got 28 minus 3n is equal to n minus 6 times n minus 6. Again, making sure that you definitely do this step right here, making sure that you write it out twice. Then foiling that out, you will get 28 minus 3n equals n squared minus 12n plus 36. N squared is your number one hint to factor. Move everything to one side with algebra, and you needed to factor n squared minus 9n plus 8. The two numbers that multiply to give you positive 8, but add to give you -9 is -1 and -8. -1 times -8 is positive 8, and -1 plus -8 is -9. So you factor it, set each factor equal to 0, and you get n equals 1 or n is equal to 8. Now it's time to test and see which one or none of them is your true solution, or both of them. So let's try n is equal to 1. Plugging it into my original equation, I will get the square root of 28 minus 3 minus 1 is equal to 6. 28 minus 3, that's 25. Square root of 25 minus 1, is that equal to 6? Well, square root of 25 is 5. 5 minus 1 does not equal 6. So n is equal to 1 is definitely extraneous. It is not a true solution to this example. Now, let's check n is equal to 8. We're going to plug in 8 into the original problem everywhere there was the letter n. And doing so, this is going to become the square root of 28 minus 24. That's really messy. 28 minus 24 minus 8 chilling on the outside is equal to -6. 28 minus 24 is 4. So square root of 4 minus 8, is that equal to -6? Square root of 4 is 2. 2 minus 8 is equal, in fact, to -6. So since it's true and it worked out, n is equal to 8 is the only solution. Bet you didn't think factoring was going to creep up on you, but yet again, I warned y'all, it keeps coming back. All right, we did it. We handled it. We're going to get more practice soon, but now you know how to solve radical expressions, specifically square roots. Bye.